In a world of new opportunities, what's the edge that's needed, not just to compete, but to win? Cisco's digital solutions for industries. In mass transit, it's a better passenger experience. In utilities, a smarter power grid for better service. In manufacturing, more uptime and improved efficiencies. And in oil and gas, safer, more secure operations. Digitize across your entire business. Connect machines, assets, and people. Break silos. That's what Cisco is enabling around the world in all industries. Are you with us?
I need to quickly occupy my locations and keep my tenants happy. An ideal building creates an environment to make this possible.
An ideal environment is one where people actually enjoy working in.
Lighting and temperature affects us physically, mentally, even emotionally. People will go to great lengths to make themselves feel comfortable.
Some of our employees bring lamps from home because they can't stand the fluorescence. You should see what goes on with who gets to sit beside the window. So yes, lighting is definitely key to the experience.
The idea of plugging lights into the network with all the computers and phones seemed odd at first.
Well, the digital ceiling connects buildings' various components. This convergence ultimately delivers a better experience.
It's like the building knows us and gives us what we need when we need it. Warmer light in the morning and cooler light in the afternoon. It even knows to pump more air into a crowded conference room. How cool is that?
Systems that used to work independently, like heating, security, lights, elevators, motion sensors, you name it. Now they all speak to each other. This really simplifies how we manage our building.
When you walk into a room, the lighting, temperature, even your phone extension gets automatically adjusted to your personal profile.
Instead of installing hardwired conduits with high voltage cabling for lights, we connect them to the Cisco network using Ethernet cables, just like voice over IP phones. This alone translates into big savings.
We stopped wasting energy. No more unnecessary heating, cooling, and lighting empty rooms.
Moves, adds, and changes are much faster. You just plug the light into the new location and you're good to go.
Making sure my properties stay competitive and occupied.
Adding a whole new set of tools for us to design and explore with.
Well, it's all about making work feel, well, a lot less like work.
There's been significant trends that fundamentally change how business interacts with customers to be more effective, efficient, and engaging. The technology transitions at play are cloud as a consumption model for IT, digitization of business, and the Internet of Things.
With the Internet of Things, data is coming at us extremely rapidly from a lot of different sources. You have to suddenly be able to bring these centers of data together to make decisions and make your company more agile.
We have the network that can enable digitization.
Cisco, through its partners and on its own, is all about connecting disparate centers of data, making architectures work, and networks and data integrate.
We have some differentiating software in the area of analytics and automation that allows you to do 4 things: to aggregate, analyze, automate, and engage.
Aggregating data is vital. Let's take, for instance, Pfizer. In pharmacology, it's important to be able to integrate data within the right context at the right time.
They've got to create new products, new revenue streams. Their researchers have a tremendous amount of data sources. Our data virtualization software enables Pfizer to aggregate that data in real time to make researchers more effective in coming up with new products that can change the world. When you think about analyze, edge computing is here to stay. One example of that is a large energy company.
They need to be able to analyze the data coming off of those wells, the temperatures, the pressure in the pipes, speed and performance of the machinery that's running those, and all of the parts.
We're providing the edge computing technology sitting in that oil well. We're also the ones to actually do the analysis of that data. But what we could do at the edge is make an immediate decision. The outcome is better efficiency, better use of their physical assets, and money.
Think of an engine constantly streaming information about how it's being used, where it's being used. You put that in a broader context and give that back to the people who are building those engines.
Something as simple as being able to know that a lawnmower is about to break. We have a platform called AIP that seamlessly connects all of these dots to improve the experience.
They could, A, build better machines that their customers are going to want to buy, B, make customers happier with their purchase decisions, and C, find opportunities that they didn't know were there.
At Cisco, we're working with stadiums. They want the fan experience to be engaging.
When I walk into one of those stadiums, the Cisco Wi-Fi network is going to recognize my phone. I'm going to be then given the opportunity that's personalized for me. It's not just that they're making it a better experience, they're making it easier to engage with that experience.
Things are going to get smarter. They're going to create a more contextual environment in a way that actually improves work, improves life and business processes.
You're going to see data markets open up in highly specialized solutions that take advantage of that data like you've never seen before. As an industry watcher, I'm excited to see it.
Here for Enterprise Networks with Guido. You are the VP for IoT. You knew that already.
I am.
Awesome. Good job. So now, today we are announcing the launch of IOX. What is that?
So IOX is really designed to accelerate the deployment of Internet of Things. Yes. And what we're doing is taking the best of internet working, which is iOS, and taking the best of open source, which is Linux, and eventually Androids and other systems as well. So you put the two together, you get iOS plus Linux, or IOX, and that's going to allow us to essentially integrate more interfaces, but also specifically run applications.
Very cool. Okay, so now I'm recalling specifically, we always say big I, little o, big T, but this is big I, big O, little x. What's up with this craziness?
A big deal. It's a big deal.
Okay.
So it's big I, big O, little x, because the x is a little bit like a placeholder for, like, you can put new stuff here. It's like variable, right? You can add more functionality. You can bring more interfaces. You can bring applications into this. Because before, if you wanted to connect to a converged IP network, but you had a serial connection or a Z-Wave connection or a USB thing or a Bluetooth low energy thing or something else, it takes a long time for other products to support these interconnects, these interfaces. And now we can get this up and running within hours, running on all of our embedded routers, starting with our CGR 1240, 819, and eventually all of our Internet of Things routers will support IOX.
Awesome. Okay, so now is this going to, I've heard of like BYOD, but are we going to have like BYOA and BYOI?
You got it.
Okay.
Bring your own interface, which really says if you have a way you want to connect, but you want to make this run across a converged network, all you have to do is show up with your hardware. If you've got a Linux driver, you recompile and go, and it should be up and running within hours. If you have an application you want to run, so this is really important for Internet of Things because there's a lot of data. In fact, in the next 7 years, we think half of Internet traffic is going to come from things. And so you can't bring all that data back to the cloud. You have to process it closer to the edge. And we want people to be able to bring their own apps and deploy them on our ruggedized routers that are closer to the edge.
Okay, so just so we're clear, because I know that, you know, other parts of the company have been launching all this SDN stuff. Is this SDN?
No, because SDN is more about programming the network.
Okay.
And the applications we're talking about are programming the data. So the data coming off the things, we want to process them, but we want to put the automation and the processing logic closer to the edge. So we're actually working on what Cisco people would call the data plane, which is the actual data coming from the sensors, whereas SDN is really trying to program the network or impact the control plane.
Okay, so is this that cloud thing we've been talking about?
No.
No? Oh.
It's even better.
It's not.
It's the fog.
Fog!
Because it's not an either or. It's about the fact that you want to do some processing in the cloud. You want to do some processing maybe at the very edge. But a lot of the times what you need is something in between. You need a traffic cop. You need something that controls a machine. And to put it all back in the cloud might take too long, might be too much data, or frankly, just not inherently secure.
Okay, so now with this traffic cop, are you applying IOX to the cop, or how does it actually work in real world?
So IOX is a framework that says, I'm going to run iOS here, so you have great internetworking. I'm going to have a container capable of running applications in a standard open source model that you understand. And then I'm going to provide you with an app store so that you can discover and download new applications, as well as an app management system that lets you start, stop, and monitor whether your apps are still running. So IOX is all of that, and it's running on the 1240, it'll be on the 819, and eventually all of our routers.
Okay, so, but how are they? How's the cop using it? Sorry.
So the traffic cop, the security model. So what we're thinking of doing is that if you think about smart cities, you're going to put this on every street corner. The applications inside of our routers will do things like coordinate the traffic lights, watch the surveillance cameras, maybe act locally in terms of turning things on or off so that you now have distributed intelligence.
Okay, so like if a cop is in hot pursuit, or like maybe a better example is like a fire truck or ambulance is like on its way, we can kind of help them.
Correct. We could like turn all the traffic lights green. We can create communication uplinks that allow them to talk to the hospital. We can also, for example, coordinate with the lighting in the city to maybe turn on all the street lights along the way to make it really bright and easy for them to see things. So these are all converged applications. They run across the same network, and some of those algorithms need to run in a distributed fashion, but there was no place to run it because you needed to run it in a ruggedized compute environment, and we have them. They're called routers.
Yay. Okay, so now are we doing this all by ourselves, Cisco, or we have some friends?
We have friends. Yes. We have many friends. So the good news is we're doing this with a lot of industrial companies who want to do this. So we have companies like Itron and Rockwell, ST Micro, and OSI Soft who've already come forward and said, hey, I know exactly what I can do with this. I've been dying to put some applications or connect some I/O modules into these devices. And Cisco, you've got a great set of internetworking products. Why don't I just add my application or my interface to what you already have? And I suspect that when we come out with this IOX announcement, we're going to get a lot more interested parties coming forward and saying, like, how do I join the party?
That's awesome. Well, thank you very much.
Thank you very much.
In general, when we talk about the cloud, we're talking about three things: data centers, cloud computing or cloud services, and virtualization or virtual computing. Though data centers can be smaller, they're generally large facilities which provide massive amounts of power, cooling, and bandwidth. Only very large organizations like Facebook or Google can afford to build their own private data centers to provide services to their users. Other smaller organizations lease space from a data center. Cloud service providers like Cisco or Amazon Web Services or Microsoft Azure offer their services out of data centers. There are two basic types of clouds: public clouds and private clouds. Public clouds offer services and applications to the general population, whereas private clouds are intended for specific organizations or entities such as governments and are only accessed by those private organizations. There are different categories of cloud services. SaaS, or software as a service, refers to on-demand software or a subscription model where the license and delivery of the software happens through the cloud. You'll find this with things like Office 365 or Adobe Creative Cloud, or even computer gaming software in which access to the software happens typically through a web browser. The software is typically not owned, but rather leased. PaaS, or platform as a service, is where the cloud service provider provides the platform, like the Java or .NET platform for a developer to develop an application or app. This oftentimes involves providing databases and tools to the developer so that they can quickly develop an app. Infrastructure as a service refers to virtual computing that can be provided over the internet on demand. This includes virtual computing such as virtual servers, as well as virtualized storage and virtualized networking capabilities that can be provisioned, allocated, and supplied on demand on an as-needed basis. Virtualization is the ability to abstract or separate the operating system from the physical hardware. To create a virtual computer, the dedicated physical hardware needs to be shared with the virtual computer. In this slide, we see a Windows 7 virtual computer that is sharing the physical dedicated resources of the host computer. This is done through a hypervisor. There are two types of hypervisors used in virtualization: a Type 1 hypervisor, known as a bare metal hypervisor, and a Type 2 hypervisor, known as a hosted hypervisor. A Type 1 bare metal hypervisor is a virtualization server. The hypervisor is an operating system that's installed onto the hardware directly, after which virtual computers can be created. There are different types of Type 1 hypervisors: KVM, Red Hat Enterprise Virtualization, Xen, Citrix Xen Server, VMware ESXi, VMware vSphere, and Microsoft Hyper-V. A Type 2 hypervisor is known as a hosted hypervisor. In this situation, the hypervisor is an application or program that is installed on top of the host operating system. In other words, you install the hypervisor like VirtualBox or VMware Workstation, Parallels Virtual PC on top of the host computer. You install VirtualBox, let's say, on top of the Windows operating system, and then you can create virtual computers. In addition to virtual computing, we can also virtualize switching and routing. In this slide, we can see two VMware ESXi hypervisors. The virtual computers are all networked together with a Cisco Nexus 1000V virtual switch. The virtual switch brings the power of a Cisco switch to the virtualized network environment. network programming, SDN, and controllers. Network programming is used to program and virtualize the network. We're talking about protocols, programming, scripting, data modeling, and markup languages, as well as architectures and APIs, or application programming interfaces. Protocols like the OpenFlow protocol, which allows a programming language to control the forwarding plane of a switch or a router, as well as netconf and restconf. Programming languages like C, C++, and Java, scripting languages like Python, Ruby, and Lua, data modeling languages like Yang, markup languages XML, and architectures and APIs like the REST architecture and API used over a web browser, and the Java API with all of its libraries and pre-written classes and blocks of code. SDN, or software-defined networking, is an approach to networking where the network is software programmable remotely. It involves the Open Network Foundation, which supports the concept and the development of SDN, and has also been responsible for releasing the OpenFlow protocol or standard, which is a protocol that separates the control plane from the forwarding plane in switches and routers. Also listed here is OpenStack, which is a software platform for cloud computing and providing IaaS, or infrastructure as a service, which means the ability to manage pools of processing power, virtualized servers, and network storage on an as-needed basis for the customer through a data center. In this image, you can see a comparison between a traditional architecture and an SDN architecture. Notice how in the traditional architecture, each device, device 1, device 2, and device 3, let's say they're network switches, each device has a control plane and a data plane. And so to configure those devices, you configure the control plane on each of those devices. In an SDN, or software-defined networking architecture, notice how the control plane has been separated from the data plane, and now the three devices, let's say there are three switches, could be controlled from a single control plane or from a single controller using the OpenFlow protocol. This way, the three switches can be programmed from a single point or a single software program. In this image, you can see this example further. In this case, the application has been developed using Cisco's 1PK Open Network Environment Platform Kit, and the software has been written in, let's say, the C or Java or Python programming languages, and the application can program the data plane on the three switches, device 1, device 2, device 3, using the OpenFlow standard. Network controllers are SDN control plane devices, which are a programmable point of automation to manage, configure, monitor, and troubleshoot virtual and physical network infrastructures. This automates the configuration of the network infrastructure. A network controller is a hardware device which locates the SDN control plane. An example of a network controller used in SDN, or software-defined networking, might be the Open Daylight platform. The Open Daylight platform is an open source SDN controller platform. You can see in this example where the SDN controller works with an application to then control the network devices, here listed as device 1, 2, and 3 at the data plane. The Cisco ACI, or Application-Centric Infrastructure, is Cisco's approach to software-defined networking and network controllers. It involves three main things: an ANP, or Application Network Policy, an APIC, Application Policy Infrastructure Controller, in this case the APEC-EM, which is the enterprise module for APIC, and switches that are application programmable, like the Nexus 9000 series switches. In this example, we can see how the Cisco APEC-EM works. The APEC-EM, or enterprise module, is the SDN controller which sits between the application and policy and the data plane devices, device 1, 2, and 3.
How did we get here? We used to keep everything in silos, nice and neat, right? We had storage, and then we had compute and network, all separate silos. In fact, compute had its own silos. Servers were local to the users, and they were grouped by function, right? We had mail servers, database servers, and so on. Then we had higher speed, wide area networks, which brought us data center consolidation, and we started moving all of our eggs into some very well air-conditioned baskets. And then came virtualization, the hypervisor. Probably our biggest jump ever for optimization. Now one server could run multiple operating systems. Applications could think that they were still siloed. Well, that then brought us multi-tenant data centers. Now compute could be offered as a service to your own enterprise or others. But here's the challenge. This hyper-virtualization has created what I call separation anxiety. You see, virtual machines grow like weeds. They're very portable, and we can do a lot of great things with them. But the network insists that your identity, and thus your policy, is tied to where you're located. Well, VLAN, subnets, security rules, and old-fashioned manual labor, these kind of things have kept it flowing for quite a while. But the complexity has reached a tipping point, and anxiety has firmly set in. Success can only be achieved when there's a harmony between the applications and the network, because they're both critical. Now, many answers have been proposed. In fact, two worth highlighting here: software-defined networking, or SDN, and network virtualization. SDN, though, means different things to different people. In general, it's some kind of abstraction between the control and the data planes, but there's a new element called the SDN controller. This is another bit of software here that should handle all the instructions between the applications and the network. This is all good work. It's interesting concepts. They're worth pursuing, but they fail to solve the problem. The SDN Band-Aid is ultimately just another layer of complexity. Now take network virtualization, which pretends the network is not really there. Just encapsulate everything on layer 3 and drive with your eyes closed. Complexity still remains, even if it is harder to see. It's just a different kind of Band-Aid. So true abstraction, isolation, and independence are needed for the network to truly support these dynamic workloads. And to truly get rid of the complexity, we need a do-over. Well, to do it over right, we need to follow a couple of requirements here. First off, the application must come first. There's no reason anything else exists except to support the apps. But also, applications cannot be touched, period. Don't touch them. And the third one, however, is keep it simple. I mean, some engineers know their apps. We got our app experts. Some engineers know their network. Both of these guys are valuable, and they need to be able to communicate very easily for this kind of thing to work. Well, Cisco's application-centric infrastructure has achieved all of this. Let's look at just 3 ACI concepts to help get you started: application network profiles, fabric, and stateless hardware. But first, what is an application? It's not as singular as you would think. A simple web application has at least 3 logical tiers. Users interact with a web tier that will then talk to back-end application and database tiers. So is that the app? No, not yet. Now you have network services functions between each of these tiers, like QoS, load balancing, security. In a nutshell, it's all the policies, right? Take Oracle, for example. I mean, it could easily have different personalities on the network. Is it development? Is it test? Or is it production? I mean, all of those look the same to the network, yet each need dramatically different policies. Well, ACI wraps all of this up in an application network profile. It's a logical mapping of how an application is going to look, connect, and be treated anywhere on the network. Suddenly, we have one simple interaction point for an app developer, a network engineer, heck, even management. Well, this policy now sticks with the app as it moves through every part of its life cycle. And when you're done with the app, all of its policy stuff disappears. None of that stuff stays on your network. It stays clean. And the ACI fabric, which is our second concept here, is made up of the Application Policy Infrastructure Controller, the APIC, plus those stateless hardware switches, our third concept. So the switch architecture is a leaf-spine layout that enables linear scalability and robust multipathing, completely optimized for east-west traffic so common to data center applications. And it scales so easily. In fact, each spine switch you add creates another network path available for load balancing. And it's a very open design, too. The APIC exposes a northbound API for access to all of the control functions. The southbound API opens up third-party network services for even more policy control. These application profiles are used by the APIC to push logical topology and policy definitions down to that stateless hardware. This is a complete reversal from traditional architecture where ties between VLANs and subnets and firewall rules are tightly coupled, trying to meet dynamic application needs. ACI is a complete system, but without the complexity. Traverse any path in the network as if it was all virtual machines with layer 2 adjacency. Seamless mobility across physical, virtual, even geographically dispersed endpoints. Top-down control, bottom-up visibility with real-time telemetry and atomic counters. It's like an overnight success, 30 years in the making. ACI makes a lot of sense.